So here we've got a guy standing on a beam. I think beams are a bit more fun than seesaws for questions like this because you never know if it's going to tip or not, and the guy's going to get a beam in his face. Seesaws are fun when you're young, but there's a little bit more danger, isn't there, with a beam tipping? Anyway, let's see what happens. So as is usual, we're going to draw a diagram. We've got a uniform beam AB of length 3.8 meters and mass 32 kilos. So there's our basic structure. The force due to the mass of the beam being concentrated at the center, which is 1.9 meters from either end. Okay, it's supported at the point A and at a point P, which is 1.2 meters from B. So let's put the supports in. And of course, those supports, the fact that the beam is resting on those supports gives us normal reactions. So those are the reactions. I'm calling them R1 and R2. You might otherwise call them RA and RP, perhaps. So we've got to decide whether the beam tips or not when this man of 62 kilos stands at a point 1 meter from B. So there's the man standing at 1 meter from B. So in order to find out if the beam tips or not, I'm just going to consider, I'm going to take moments about P, because that's the point that it might tip about. And I'm going to look at these two forces here and see what the balance of these two forces is. So if we look at the clockwise moments of those two forces, it's 32G is anti-clockwise and the 62G is clockwise. So the resultant moment is minus 32G times its distance, this distance from here to here, 0.7, plus the 62G times its distance, which is 0.2. So the resultant clockwise moment is minus 98 Newton meters. If that was a plus figure, then that moment would be clockwise, that would be making the beam tip. But since it's not clockwise, it's not positive, it's negative, that means that the resultant moment about this point is in the anti-clockwise direction, so the beam won't tip. So the guide's going to be happy about that, I'm sure. So what about part B? The smallest distance from B that a 40 kilo mass could be placed without the beam tipping. So let's put this mass in a place X meters from B. So it's 40 kilos, so that will produce a force of 40 G newtons. And what we want to do is we want to make this mass, make this distance as small as possible. But the smaller we make it, the more likely it is that the beam is going to tip. In order to make it as small as possible, we want the beam not to tip just, which means that this reaction will be going down to 0. The smaller we make this distance x, the smaller this reaction will become. And the critical point is when R1 equals 0, but the beam is still in equilibrium. So we can then look at P as our pivot point. We could take moments about any point, but I'm going to take moments about P. And the clockwise moment will be equal to the anti-clockwise moment. So the clockwise moment, we've got the 62G and the 40G. The 62G is got a distance of 0.2. The 40G has got a distance of 1.2 minus x, and that equals the anti-clockwise moment. We don't need to worry about this force because we've just said that R1 equals 0, and then this is the force which creates the anti-clockwise moment, so that's 32g times its distance, 0.7. So when we solve that equation, we get a value of x of 0.95 meters. Okay, so that's parts A and B done. What about part C? Now, part C is talking about the 40 kilo mass being removed, and the man standing at a different point. So I think we need to have a new diagram. We're putting a mass at A to prevent the beam tipping. So let's call the mass X. Sorry, the mass M, we'll call it. So the mass at A is going to produce a force of M times G. So here's the man now standing at B, and the 40 kilo mass has been removed. Okay, so we want to make the mass, we want to find out what this mass would be in order to prevent the beam from tipping when the man steps on the beam at B. So once again, we want R1 to equal to 0. So the clockwise moment will equal the anti-clockwise moment again. And clockwise moment comes from just the man, 62g times 1.2. And then we've got anti-clockwise moments from the 32g and the mg. So 32g times its distance and mg times its distance from P. So when we work that out, we find that M is 20 kilos. So there's part C. Part D is the question about assumptions. So as is normally the case, we model the beam as a rigid rod and the man and the other masses as point masses. So there we are.